Unfortunately, the first speakers, Leonardo Salvatore Alaimo, couldn't come because the wife had an accident, a crash with the car, and so he couldn't come this morning. So we have to move to the second. We have to move to the second speaker. The second speaker is Paolo Giordani. He will present a paper together with Roberto Rocci and Giuseppe Bove on the Parafac model in the maximum likelihood approach. Parafac, as you know, is a three-mode model for three-way data. So please, the floor is yours.
Yes, thank you, Maurizio, and thank you for inviting us to give this talk. Yes, as you told us, the talk is on the Parafac model. And the Parafac model is a way to analyze three-way data. Three-way data occur very frequently in several domains of research. Here you can see some examples. And the common aspects of all of these examples is that the same variables are collected on the same units in several occasions. And this means that, this implies that the data are no longer stored in a matrix, but are stored in what is called an array or tensor, a sort of box that can be obtained by collecting all the unit by variable matrices corresponding to the various occasions. And to handle in a proper way the elements of the array or tensor, we need a third index, k, able to take into account the occasion, the generic kth occasion. So the generic element of the array is xijk, giving the score of unit I on variable j at occasion k. Now the point is how to analyze such a new kind of information. And maybe this one may try a natural way to handle this array is to try to convert it into a matrix, trying to transform the information stored in the array in something stored in a matrix. And in principle, this can be done. There are several ways to do it. A simple and probably the most common way is the process leading to the so-called Supermatrix XA. The process of converting an array into a matrix is called matricization or unfolding. And for instance, in order to obtain XA, the idea is very simple. We have k unit by variable matrices. Simply juxtapose next to each other all these matrices. And so we get a matrix with I rows, where the rows refer to the observation units, and j times k columns, referring to all the combinations of variables and occasions. So we have a sort of new variables referring to all the variables in all the occasions. This is not the only way to define to obtain a two-way matrix starting from a tensor, from an array. There are at least other two ways known as variable mode unfolding or occasion mode unfolding. By the way, the main point to discuss is whether by converting arrays into matrices, in particular into supermatrices, we need some new tools for handling three-way data. For instance, if we want to summarize a matrix, it is well known that PCA is a powerful tool. And so the question is, can we apply PCA for analyzing in a proper way a supermatrix? The answer is no, and the reason is that if we apply PCA to a supermatrix, of course this can be done from a mathematical point of view, but in doing so we miss the fact that we have a collection of variables repeated in different occasions. And so we miss the three-way structure of the data. For this reason, PCA has been extended by at least in at least two ways, according to at least two models. The most common, and these models that are the most common ones are called the Tucker tree and the parafac. The Tucker tree is the more general model. Is more general than parafac, and the Tucker tree consists in looking for P, Q, and R components, so different groups of components, for the units, for the variables, and for the occasions. And so this consists in finding three latent component matrices for units, variables, and occasions, plus a new, actually it's a supermatrix, so a new tensor called core tensor or core array, holding the interactions among the components of the various modes. The presence of the core makes the model quite complex to handle. It's not clear the interpretation of the core elements. It's not clear how to relate the components. And for all of these reasons, the simpler parafac model is usually preferred. The parafac is the more natural extension of PCA, the more natural three-way extension of PCA. And actually, why it's very natural? Because if in PCA we have two matrices, two latent component matrices, one for the units, the scores, and one for the variables, the loadings, respectively A and B, the idea of the parafac model is simply to add a new component matrix for relating the occasions to the components. So we have several occasions. We relate the occasion to the components, and this leads to a model that can be formulated according to this formula, where this symbol denotes the Catril-Rao product, and C Catril-Rao B allows to fit in a proper way the three-way nature of the data. The parafac and the Tucker, but now the talk will be focused on the parafac model. The parafac as well as the Tucker T model are usually seen as extensions of PCA, and indeed I introduced them as extensions of PCA. However, in the literature there are some papers trying to extend the parafac starting from factor analysis. However, before introducing the parafac by considering factor analysis, I would like to mention a useful property of the parafac seen as an extension of PCA, and therefore called component-based approach. The parafac solution is uniqueness up to a scaling and a permutation of the columns of the matrices A, B, and C. And such a uniqueness property has been proved by several authors, but the most useful proof is the first one offered by Kraskal in 1977. The proof is based on the concept of K-rank. The K-rank of a matrix is something related but different to the concept of rank of a matrix, and is defined as the largest number K such that every subset of k columns of Z is linearly independent, where Z is an arbitrary matrix. Now, the uniqueness of parafac holds if the k ranks of the three component matrices A, B, and C, if the sum of these three ranks is larger than or equal to 2 times S plus 2, where S is the number of components. Such a condition is very mild. It holds for almost all real data. And indeed, the parafac solution is therefore unique. And this is very, very useful in several domains, especially in life science, because the latent components often have a physical meaning. Now, by moving to the approach called structural-based, trying to extending the parafac, trying to extend in the factor analysis model, we have an alternative formulation of the parafac. This is the formulation with S factors, with S common factors. And we can see that it is closely related to the factor analysis formulation. The main difference is that the factor loadings in lambda are now replaced by C catenary B. So the parafac can be seen as a standard factor analysis model where the factor loadings are constrained by C catenary B in order to take into account the three-way nature of the data. Actually, this formulation leads to a covariance reparametrization of the covariance matrix as it is for the factor analysis. And the parafac covariance structure is very similar to the one obtained by using standard factor analysis. Of course, in this case, the covariance matrix refers to all the combinations of variables and occasions. And so we have J times K specific factors referring to all the combinations of variables and occasions. In practice, there are at least other two differences between factor analysis and parafac. So the covariance structure looks quite similar, but some differences that are not easily visible exist. The first one is scale invariance, concerns the scale invariance property of factor analysis. Factor analysis, the standard factor analysis, is scale invariant. If we rescale the variables, we can simply rescale the factor loadings. This is not the case for the parafac. And this depends on the fact that the loadings are constrained, have a structure involving the Catenary product, and the Catenary product gives some problem in order to make the model scale invariant. For this reason, there are some extension, at least two extensions of the parafac in order to make it scale invariant. And one of them consists in pre-multiplying C catenary B by a positive definite diagonal matrix D. And the role of D is to absorb the scaling of the variables. There is one more difference involving the covariance structure of the specific factors. And there are at least three ways, or at least we focus on three different kinds of covariance metrics for the specific factors psi. There are at least three possible structures. The one very similar to the standard two-way case where psi is diagonal, so the specific factors are uncorrelated. But at the same time, since we have the same variables in the same occasions, we can allow some dependencies, some correlations between the variables in the occasions and between the occasions with respect to a given variable. And so this this leads to other two structures for psi. In particular, psi can be block diagonal when the specific factors are within occasion correlated, and banded when the specific factors are within variables correlated. And now, the point the research interest we had, and we tried to solve, was whether the parafac solution is still unique under this new structural approach. So if we see the parafac as an extension of factor analysis, we investigated whether the uniqueness of the solution still holds. And if it holds, under what conditions, when it holds, what can we say on that? And actually we proved uniqueness considering different levels of complexity for the parafac model. Of course, I will not give the details of the proofs. I simply try to give you the ideas behind the proofs. And I start with the simplest case when where psi is diagonal, so where the specific factors are uncorrelated. And I start with the case in which the parafac is not scale invariant. This is the case more similar to factor analysis. And therefore, in order to prove uniqueness, we combine the classical condition of uniqueness for the parafac with the standard results of uniqueness for factor analysis proved by Anderson and Rubin in their seminal paper. And so the main idea of the theorem is that if we have two parafac solutions, if this condition, if any row of C category B is deleted, there remain two disjoint submatrices of rank S, and this is the condition given by Anderson and Rubin in theorem 5.1. And if the classical condition holds, then the solution is unique. A comment is needed for the classical condition, because in the previous slide, I introduced the classical condition considering the K-rank of the matrix A. But in this formulation, the matrix A and its K-rank disappears. The reason is that the K-rank of that A is in practice replaced by the covariance matrix for the common factors phi at the power of 1/2. This matrix has a full column rank. And its K-rank is equal, therefore, to S. And therefore, the formulation of the classical condition looks like S plus K-rank of B plus K-rank of C, higher than or equal to 2 times S plus 2. And so in practice, we simplify S on both sides, and we obtain this formulation. This formula. This a sort of simplified formula for the classical condition when one matrix has a full column rank. We now move to the case in which psi is no longer diagonal, and so we move to the case in which we assume some correlations among the specific factors. We consider the block diagonal case, but the proof is similar for the banded case. And in this case, we replace the condition given by Anderson and Rubin with this condition involving the rank of B diag CK, where diag CK is a matrix, is a diagonal matrix having the row K of C in its main diagonal. And this condition that must hold the rank of B diag CK must be equal to S for at least 3 occasions, is used by Brown in a paper dated 1980, and this paper is about factor analysis for multiple batteries of tests. Factor analysis is a specific case of multiple batteries of tests if every battery has only one test. So it's an extension of factor analysis for multiple batteries. In this case, we combine the results by Brown with the classical condition, and once again we obtain a proof of the uniqueness of the parafax solution. These 2 results are based on consider the case in which the parafax is not scale invariant, and so it remains to prove what happens for the most interesting case when scale invariance holds. In this case, we mix the previous 2 results depending on the structure of psi, but here the point is the key point of the proof is how to use the previous results in order to prove uniqueness for the scale invariant version of the parafax. The scale invariant version of the parafax involves the use of the matrix D, and the key point of the proof is to show that when psi and psi n, the two parafax solutions, are equal to the identity matrix. I forgot to say that this is a condition of the scale invariant parafax. If this holds, the matrices D and Dn are equal, and therefore we can simplify them, and this allows to go back to the previous results. And so we can apply the previous results upon showing that this holds. So uniqueness holds for the parafax model according to the structural-based approach, and therefore, given this result, we analyze its performance in practice. For this reason, we considered a 3-way data set involving 68 children with respect to 4 personality variables and measured by 3 judges. This is an example of multi-trait, multi-method matrix, and in practice we deal with the correlation matrix for the 3×4 combinations of variables, traits, and judges methods. We fit several scale invariant parafax models to such a correlation matrix, assuming the multi-normal assumption, and we considered several models varying the number of factors equal to 2 or 3, assuming orthogonal or oblique common factors, are assuming different structures for psi, so for the specific factors, in particular diagonal, banded, and block diagonal. And we selected the best model according to the common information criteria and according to the significancy of the model. We see that the models are significant if we consider three factors, so the two-factor solution is too simple to summarize the data in a proper way. And among the 4 significant models, we select the one with the lowest AIC. There is a contrast with respect to the one suggested by the BIC, but we discard this model because it is not significant. We therefore focus our attention of this model, and this model refers to the case in which the common factors are orthogonal, and to the case in which the specific factors are within trait correlated. So there exists some kind of correlations between the specific factors, a kind of correlations that cannot be captured by the standard factor analysis model. We give an idea of the interpretation of the solutions, of the solution, in particular of the factors. And actually, the interpretation is quite similar to factor analysis. That is, we should look at the loadings with eigenvalues in absolute sense. But the only attention to be paid refers to consider both the matrix B and the matrix C. And for instance, if we consider factor 1, if we interpret factor 1, we can see that that factor 1 with respect to the traits is mainly related to the duality between the variable extraversion and the variable academic achievement motivation. And this duality is mainly measured by peer report, which is the method with the highest loading. You can see a lot of ones in the first rows of B and C, because without loss of generality, we impose such a constraint in order to estimate the parameters. The interpretations of the other 2 factors are quite similar and are reported below, but it does not present particular problems with respect to factor analysis. And so, to conclude, this talk is about the Parafac model for 3-way data. The Parafac, we saw the Parafac as an extension of principal component analysis as well as of factor analysis. The literature is mainly devoted to the PCA approach, but we believe that the factor analysis one is very useful, especially for the scale invariant property. And therefore, we analyzed whether uniqueness that has been deeply investigated for the PCA approach still holds for the factor analysis version. We saw that we proved that this holds. That uniqueness holds under various kinds of correlations among specific factors. And so we hope that this result stimulates the use of the Parafac according to the factor analysis approach, according to the structural-based approach. In the future, the improvement is very technical. The idea is to consider other sufficient conditions for uniqueness. The results we found are based on the classical condition. It's the most common one and the most famous one. But there exist in the literature several refinements of the uniqueness condition. And so it makes sense to make things more elegant by considering other conditions. That's it.
Thank you.
Thank you.
We have time for some questions or comments. Maybe I can start to open the discussion. In factor analysis, you have a special case in which the variance and covariance matrix is diagonal, and then you get, as you know, the probabilistic framework probabilistic principal component analysis, you get the solution of the factor analysis. Now, the factor analysis corresponds to the solution, in this case, of principal component analysis. Do you have a similar case in this context? So because we have now two solutions. One is the factor analysis solution in estimated the maximum likelihood framework, and the other one in the alternating least square solution, least square solution. So you have this is the first question. The second is the uniqueness is the non-uniqueness of the solution in factor analysis is used to rotate the solution in order to have a possible better interpretation of the results. Rotation uniqueness. In this case, you have the uniqueness solution that is easy to be interpreted.
Okay, now concerning the first question, actually as far as I know, three-way probabilistic extensions, three-way extensions of PCA are not. I don't think they have been developed. We prefer the factor analysis approach because the solution is scale invariant. In PCA, even in the probabilistic case, this is not the case as far as I know. So we believe that if we adopt a probabilistic approach, factor analysis is should be preferred. Well, concerning the rotations, the possible rotation, perfect is in general preferred for the simplicity, for the uniqueness of the solution with respect to the Tucker. Tucker is in general applied in psychometric in the psychometric domains where the components do not have a physical meaning. So I think this makes a relevant distinction between the two models.
Thank you. Do you any other comment? If not, we can thanks again all of Dani. Now we have the second speaker. Second speaker is Carlo Cavicchia from University of Rome La Sapienza. This is a joint paper with myself and Giorgia Zaccaria. And the title of the paper is Dimensionality Reduction via Hierarchical Factor Structure. Thank you.
So good morning to everybody. First of all, I want to thank Professor Vighi for the invitation. It's a pleasure to be here to present my last work with Professor Vighi himself and my colleague Giorgia Zaccaria. My presentation is divided by 5 main parts. First of all, we'll see the motivation has led the work. Then we'll introduce our model with its estimations and properties. Then we'll see a simple and small simulation study. Then we'll introduce the bench-told dataset and an application of our model on it, and then some conclusion and a recap. So why do we need a hierarchical structure as dimensionality reduction? Because many relevant multidimensional phenomena are defined by nested latent concept. So we can represent and we can study this hierarchical structure by a tree structure. It is possible to investigate the hierarchical data correlation structure through an ultrametric correlation matrix. And then we can use this strict relationship between a non-negative 2Q minus 1 ultrametric correlation matrix and the hierarchy of Q latent concept to build the general concept and the general indicator for this phenomena. The most used method for dimensionality reduction is the PCA, but PCA is not able to catch the hierarchical relationship among variables. And for example, in this little generated data set, we have 10 manifest variables grouped in 4 groups. We can see that the second and the third group are the most correlated among them, and then the fourth is correlated a bit less, but is the third in order, and then finally we can group the first one in order to define the general indicator. So here the hierarchical structure is clear. We know the order of the aggregations, but PCA is able to get only 2 components. So we have no information about the hierarchy, and we have no sparsity on the loading matrix. So we have no clusters of manifest variables. Our idea is a model that is able to get the right partition of the manifest variables and then all the aggregations in the right order by the level of correlations in order to define the general concept. Here we can see the path diagram of our solution where the manifest variables are grouped in the lowest part, and then all the latent concept, and in this sense the indicators are defined step by step. So assuming that each cluster of variables represent a latent concept, we can build the reliable indicators which compose the general composite, the general concept in this case. To do that, we need to detect 2 important features, 2 crucial features. The first is the internal consistency of a concept, and the second is the correlation between concepts. The first one is the global consistency of a group of manifest variables. This is computed as a function of the correlation within cluster. It is also known as internal reliability. We'll see in our model that we aggregate this information about the internal consistency in a diagonal matrix Q by Q called RW. The correlation between concepts is calculated as a function of the pairwise relationship between the items of 2 different clusters of manifest variables, and it's so important because it defines the level of aggregations. So it's our way to define the order of aggregation of the starting clusters of manifest variables. The correlation between Q concept might be summarized in a Q by Q correlation matrix RB. So we have the aim to reconstruct a correlation matrix R that is composed of only non-negative values via an ultrametric hierarchical structure, which is able to highlight the 2 features that I already presented. The model includes the matrix RW, so the matrix of the internal consistency, RB, so the matrix of the correlation between concepts, and the membership matrix B. The membership matrix B must be binary and row stochastic, whereas the matrix of the correlation between clusters of variables or concepts, RB, must be ultrametric. Now, in order to study the properties of our model, we have to clarify the fact that the part of the model, because the model is composed two parts, the model and the error. So the matrix P that we already seen in the question 1 can be rewritten in as in the question 6. It's important to underline that this matrix is ultrametric and it is actually a proper correlation matrix. The ultrametricity is easy to demonstrate because the matrix Q that is defined like RB minus the identity matrix in order Q plus RW and its extension in the J dimensionality are ultrametric. So P respects all the conditions to be an ultrametric matrix. We know for the condition to be a correlation matrix that a symmetric diagonally dominant real matrix with non-negative diagonal entries is PSD. So P as a matrix that is diagonally dominant is non-negative on the diagonal. Actually, all the values are equal to 1 and is real. So we know that P is PSD. Its diagonal is composed only by value equal to 1, so P is a correlation matrix. So we have demonstrated that P is an ultrametric matrix and a correlation matrix as well. Now, we have talked about two important features, and now we propose two measures for both of them. The first one is the measure of the internal consistency, and we propose the least square estimation of the matrix RW that we have introduced already as a function, as a measure of internal consistency. It is function only the membership matrix and the correlation matrix, so the data matrix that we have, that we want to reconstruct. The measure for the correlation between class of variables, so the correlation between concepts, is given in a matrix that is the least square estimation respect to RB in the model 1, that is function of the correlation matrix R, the membership matrix V, but also the estimation of the matrix of the internal consistency. So, in order to have the estimation, the least square estimation of our model, we propose a coordinate descendant algorithm composed by two main steps. After the initialization, we have two main steps. The first one is the computing of RW and RB. So, given the current solution for V, we can estimate these two square matrices according to the estimation that we already seen together. It's important in this step of the algorithm to verify that RB is a proper ultrametric matrices. Otherwise, we have problem in the definition of concepts. The second step is the assignment step, so it's the solution of assignment problem where we assign each variable to each cluster of our Q structure. The stopping rule is when our objective function converge. Our objective function is for sure the least square function of our model, the model 1. In order to assess the performance of our model, I'll present a simple simulation study where we have only two scenarios. The first one is considered as the low dimensionality. We have only 30 manifest variables, and Q, the number of concepts, the latent concept, so the concept at the bottom of our hierarchy, is equal to 4. In the second scenario, we have J equal to 100 and the same number of Q. The matrix E, so the matrix of the error, has been generated from a multivariate normal with the dimensions uncorrelated, and the level of error was managed by the variance of this error. It's important to notice that we have to handle the problem of that when you add an error to an ultrametric correlation matrix, it's possible that you get in a non-proper correlation matrix. So we have to face this problem. We tried a few possible solutions, and for this simulation, we consider the matrix, the generated matrix R as a covariate, so a variance-covariance matrix, and then we rescaled this matrix in order to get in a proper correlation matrix. The result of our simulation are pretty good for both of scenarios. With small error, we have impressive results. We are able to get the right partition, so the right classification of variables in Q concept, always in the right way, and also the MSE of RW and RB are really good. For large error, we have not the perfect partition in all the cases, but the performance are quite good as well. Now we'll see an application on the Bechtel dataset. The Bechtel dataset is a dataset composed by 17 variables. It is proposed as a correlation matrix, and the dataset is proposed with 6 latent concepts. So our goal has been to correctly estimate the variable partition by identifying the 6 latent concepts. There are memory, verbal, words, space, number, and reasoning. We are in a psychometric framework, so we are studying skills and attitude, mental attitudes of individuals. Then, after identifying the right partition, we were interested to get in the right hierarchical structure of these latent concepts in order to identify the general concept and, if possible, the general indicator. These 17 variables are divided quite in a balanced way. Only memory has 2 variables. All the others has 3 variables inside. We can observe on the left the observed correlation matrix, so the Bechtel correlation matrix, and on the right we can observe the our model, so the estimated correlation matrix that is ultrametric, and where there are evident the 6 clusters and the levels of aggregation. It's important to notice also that we need that the correlation matrix, so the Benchtold correlation matrix, was composed only by non-negative values. So the algorithm has found the right partition in same main groups corresponding to the theoretical ones. So the solution is correct. And even using the Cronbach's alpha in order to measure the reliability of this latent concept, we can observe that all the concepts except memory are reliable. So the value are larger than 0.7. We can spend some moments to understand why memory is not considered reliable. The problem in the case of Cronbach alpha is that when you have too many indicators, the value of the Cronbach's alpha is always low. So in this case, even the correlation between the two variables, first names and word number, are quite large. We have value of the Cronbach alpha lower than 0.7 because the items are only 2. So this is our solution. We have a path diagram where the first two latent concepts were joined are verbal and reasoning, and then one by one, all the latent concepts add information in the definition of our general concept. So the shape of our hierarchy is something like step by step, because every group of variable is adding information at the same enlarging group of variables. But it's possible to underline three main concepts. Intellectual abilities composed of the concept verbal, reasoning, number, and words. And then memory and space. There are two latent concepts composed by only, they are corresponding to the theoretical ones. It is evident that the existence of the general concept which may represent the dimensional mental abilities. So in this case, we have the perfect example to show how it's possible to define a general concept starting from Q reliable latent concepts. Some conclusions in order to recap what we seen in this presentation. We have presented a novelty model for non-negative correlation matrices which detect Q latent reliable concepts, compose them in order to find the general concept. This is useful. In this case, this model is taught in order to reconstruct a correlation matrix, but it is possible to quantify this latent concept in order to build composite indicators or any numeric evaluation of these concepts. The whole hierarchy of latent concept is built by the level of correlation. It is possible because if you start from all positive values of correlation, so our matrix R is composed by only positive items, you can define the two features that I presented, so the internal consistency and the correlation between matrices, with two measures that are the main topic of my presentation. There are relative measure because they are between 0 and 1. So it is possible to use, in this case, the correlation between concepts to define the level of aggregation. Our model investigates in depth the non-compensatory hierarchical structure of the latent concepts. Also in this case, the non-negativity property of R is crucial, because otherwise we could have the problem of variables that compensate themselves. So we found the ultrametric correlation structure for the model allows to disclose the parsimonious hierarchy from the manifest variables up to the most general concept, and then we propose the LS estimation for this model. Like future works, I want to propose myself to build a more exhaustive simulation study in order to assess the performance of this model in many situations. Even if restrictive, the non-negative assumption turns out to be realistic in manifold applications, but our goal is to extend the result to a generic correlation, maybe find new measure of internal consistency and new measure for the correlation between concepts, and the development of a criterion for the choice of Q that is something that is not subject of this study for now. Thank you for the attention.
Thank you very much. We have some time for questions or comments. Yes, please. Francesco.
Probably it's a silly question, but any correlation matrix can be easily transformed into a distance matrix, and then on this matrix we can perform hierarchical clustering. So the curiosity is to have any comparison between this approach and the most
Not for now, actually. This work was focused on the building of a measure for the internal consistency and the correlation between clusters and concepts. So, no, for now we didn't test this model against the others yet.
If I can add also a comment, the idea is to take a sort of distance between what it is clustering method. Yeah. Yeah.
So these two steps should be in both directions.
Yeah, technically you can indeed transform a similarity matrix, which is a correlation matrix, into a distance, and then find the closest ultrametric matrix to the given similarity matrix. So this is true, but the idea was indeed, as you have seen, we have not used the representation of a dendrogram just to take a distance between what we are doing with respect to a clustering. The byproduct, final byproduct is indeed a clustering structure of the variables, but actually what we are trying to stress, to underline, is the idea to have a hierarchical set of concepts and to use the same typology of methodologies that we use for analyzing factors and latent concepts. So this is the point. Any other comment or question? If not, we can thank again the speaker, and the session is over. Thank you.